One of the most important things to know in this course is to know how to show that an operator is bounded linear. And this exercise is from the slides, the lecturer slides. So this question is, define f as a map from the continuous, this C with the subscript infinity means the continuous functions between the closed interval a and b to a field of real numbers, that's R, by f of x equal to the integral from with interval a to b of x of t dt, x t dt. So from this question, they've given us this functional. We know that f is a functional because it's going from a space to a field, right? And they've given us the interval that it is on. They've given us a lot of information in this question. They've also defined what f is to us. Now, they said for each x in x, show that f is a bounded linear functional and that the norm of f is equal to b minus a. What this question is telling us to do is to show that f is linear, show that f is bounded, and also estimate the norm of f. If you watched one of the previous videos, we did something about estimating the norm of f. That's the same thing here, but here they've given you what the estimate is already, but they want you to show it. So they want you to show that this norm of f is equal to b minus a. Now we're going to start with the first part of the question, which is showing that f is bounded linear. Whenever I want to show that something is bounded linear, I always like to start with linearity first, because proving that something is linear is easier to me than proving that it is bounded. So just start with the easier part. You can do this either way. You can start from boundedness to linearity, but for the sake of this, I'll be starting from linearity. So firstly, I've decided to let x be equal to this space here. That's the space of continuous functions within the interval a to b. So just to make my work simpler, pretty much, that's why I'm doing this step. So now I can now replace this entire thing with x in the map. So f is an operator from x to r. So now I want to prove linearity. So we start with for x, y in x and alpha, beta in r. So we are picking our xy from the space, our scalars from the field. So we must show that f of alpha x plus beta y is equal to alpha f of x plus beta f of y. This, also in my previous video, we spoke about this, so you can watch it just to understand better. This is this is the proof of linearity. You just have to always prove this whenever you want to show that an operator is linear. So we'll start f of alpha x plus beta y. We'll go to what we defined f of x as. Wherever we see x, we're going to put alpha x plus beta y, because here we have x, here we have alpha x plus beta y. So now we replace x here with alpha x plus beta y. So now we now have, that's the integration from a to b of alpha x plus beta y of t dt. Now, you agree with me if I say that I can share this t with alpha x and beta y. So I open the bracket, I expand it. This becomes alpha x of t plus beta y of t dt, right? We are still following the same step. So after this step, I can now bring out this alpha out, and also divide the integration. I can split the integration into two. So that gives me this next step. So I have alpha of the integration of from a to b x of t dt plus beta. You bring up beta here. Since beta is next to y, we are going to have y inside this integration. So we have alpha of x to t dt, then beta times the integration of yt dt. If we go back to the question, you can see that this looks familiar. This is the same thing as f of x, and since we have y here in the place of x, this is the same thing as f of y. So we can now say this is alpha f of x plus beta f of y, just by how we've defined f of x earlier. And since we've been able to move from here to here, we've proven that this is equal to this, hence we can therefore say that f is linear. We've proven linearity, which is the first part of the question.